Okay, we are live. Hello, everybody. Good morning from the United States mountain area. My name is Bryan Gillespie. I'm a research cryptographer at Inversed Tech, a new cryptography consulting group. I'll be co-presenting with Ying Tong Lai from Geometry Research about a research project that we've done in collaboration with Daniel Benarroch, who's my boss at Inverse Tech and CEO, as well as Andrew Miller at UIUC. Shout out to the Zcash AV Club for doing a great job on the presentation for this conference. It's been going really well. I'm loving watching some of these talks. We're going to be talking about a research project based on a grant from the Zcash Foundation about programmable privacy. So this is a systematization of knowledge project, trying to understand kind of the state of the art on programmable privacy throughout protocols that are being developed and researched kind of at the cutting edge of the idea space right now. So our goal here is to survey and systematize blockchain privacy solutions, kind of focusing at the operational level. There's a lot of variations and technical details that go into making any privacy solution, as Zcash community members know. But our goal is to try and identify the big building blocks that go into producing privacy solutions of these sorts. So in particular, we wanted to kind of understand the big picture of how these privacy techniques come together, and also to assess the suitability of kind of these various solutions for how they might be used in the Zcash protocol or the ecosystem more generally. In more detail, we're looking at surveying a large collection of contemporary, trustless, distributed privacy protocols, and identifying the ways that they support privacy in their implementation. And in particular, how they provide some generic notions of programmability while allowing privacy in the execution of these application designs. We were aiming to define a framework for analyzing protocols and categorizing these privacy techniques in a kind of generic way that can be compared between protocols in some nice way. We wanted to identify architectures and features which work well together, kind of having a global bird's eye view of these architectures gives a good opportunity to try and think how the pieces fit together and what benefits of various techniques can be synergistic. And finally, we decided that we wanted to formulate recommendations for the Zcash protocol for community development based on what we found. So what did we find? Well, okay, first of all, here's a list of privacy protocols that we reviewed in various levels of detail at various times in our study. This is a fairly long list, but fairly unstructured as described here. We'll talk a little bit more about how this can be organized based on our framework a little bit. But the bottom line is that there's kind of a wide variety of different types of protocols that we took a look at, including protocols that are under development and design and on the way to productization, some that are just prototype implementations of interesting ideas, and some of which are just architectures described in the research setting. Our emphasis when designing our framework was to accommodate the design developments that are on the more practical implementation side of things. So the protocols that are actually putting together solutions right now, as a way to emphasize solutions that show promise for being kind of concretely applicable in the near term for new designs. But we tried to consider a wide variety of sources for these techniques that are being used for programmable privacy. So the first thing that we noticed as we were doing our study was that there's a really common architecture that the Zcash community will be very familiar with, which is this notion of off-chain plus on-chain computation. Okay, it's exactly what Zcash uses as its basis for shielded pools. And it involves two phases of computation, what we call the independent computation and the global computation phases, which roughly take place off-chain in the client software privately, and then on-chain in the validator set. So at the start, the client does off-chain computation over wholly owned private data. So this is your Zcash notes are computed on, and some logic is checked to generate output notes of a shielded transaction. Private data that needs to be part of the application state is witnessed on-chain via commitments in a Merkle tree. Data and computations are confirmed by use of ZK snark proofs for correctness. And finally, once all of that is packaged together and the relevant proofs are transmitted to the network, then validators do some on-chain computation based on what's submitted, which can be as minimal as updating a nullifier set and updating the commitments, but can be more complicated in a more full-fledged programmability architecture. So the pros of this architecture and what makes it very widespread in solutions that are currently being deployed out there are excellent privacy properties. So the privacy of this independent computation phase only depends on the individual security of the client node that is doing the computations, and has nothing to do with the network overall. And additionally, because of the way that ZK snark proofs have been advancing over the last number of years, there's a lot of programmatic flexibility. Snark proofs are just exploding in usefulness in terms of their efficiency and in terms of the tooling available for them. So application development is just becoming easier and easier. I like to think of this as kind of the ZK thesis architecture that became popular a few years ago, and it still is rolling onward, and a lot of awesome solutions out there being developed. Some of the cons of this architecture, as also have been observed in various settings in the Zcash ecosystem, state bloat. So this architecture of using Merkle trees to represent commitments is very good for privacy, but the problem is that you can't tell which notes have been spent. That's kind of the point. And so you don't know which notes can be pruned from a state tree, and you just have to keep track of all of them in the naive implementation. And likewise, trial decryption is an issue that Zcash has grappled with, where if you want to find encrypted notes that have been addressed to you and you don't have any other signaling method to learn which notes are for you, then you just have to check whether you can decrypt every single shielded note that's submitted to the network that gets generated. And so this linear scaling with the throughput of the network is not great for especially light clients. These two cons in particular have growing issues if you increase the scope of this privacy mechanism to general programmability, because more applications means there's more state commitments and more encrypted data to trial decrypt. And so it's an ongoing question, like what the best ways are to address these issues in terms of performance. The last con on this list is what I think is one of our most interesting realizations from this study, and which we'll discuss in more detail as we go, is the notion that this private computation phase, this off-chain computation, is really intrinsically single party. And what that means is that when you're constructing ZK snark proofs, one of the basic ideas for kind of the standard snark proof constructions is that you need to know all of the details of the computation witness. And that means all of the inputs and all of the intermediate computations have to be known by the prover who's generating this snark proof. And that means that there's only one privacy regime for the prover, which is they see everything. And so if you're working over data that's fundamentally your own private data, then that's great, because there's no problem with you seeing all of that data. But if you want to try and use the private information from multiple parties in one of these computations, you run into trouble. Like, this is not what ZK snarks are designed for in their basic form. So looking at protocols that are using this kind of ZK thesis architecture of off-chain and on-chain computation, what we noticed is that there's a pretty wide variety of trade-offs that can be made in the design space. Our observation is that really the baseline for providing kind of the fundamental tools to support privacy-preserving applications on a protocol are fairly low. All you really need is a generic support for a verifiable computation engine, so some generic ZK snarks, as well as the ability to represent Merkle roots. And once you have those two pieces, that's enough to really support privacy-preserving applications for a sufficiently motivated developer. Okay, and this last point I think is a really fundamental issue. And the question is, what degree of built-in support should a protocol provide for various aspects of development that are involved in private privacy-preserving applications? And so we found a few axes that show some significant variation in these designs. One is the degree of permissionless application programmability that is even provided by the protocol. And the question that you have to ask is, well, if you're allowing anybody to permissionlessly deploy an application on the protocol, what are the standards of quality and user experience that are provided by those applications, right? There could be scams deployed on the network. There could be poorly vetted protocols in terms of security. But opening up application design to a broader community also enriches the overall space of products that are available. So there's a real trade-off as far as what the user experience is that a protocol wants to provide to users, kind of what the baseline guarantees on security of applications that are deployed are. Beyond this basic question of how much programmability is provided for, the other question that really shows some variation is how many resources in terms of compute are provided by the validator set, both in terms of computation, so how much of a full-fledged virtual machine is provided for on-chain computation, as opposed to just specialized specific computations like updates of account data or some restricted computational model, and especially on-chain data storage, which of course is an issue for all blockchains that are providing some generic computation. How do you handle both allocating and charging for the service of data storage on the network? A few protocols that kind of exemplify these variations in the design space here. Aztec is developing an Aztec protocol, which is aiming to really be a full-fledged programmability layer. Think Ethereum, but with off-chain computation built in. And so they provide a nice domain-specific language, the Noir language, which gives a very nice developer interface for private programmability applications, as well as providing a full virtual machine and on-chain storage for data. So kind of they're aiming to be the full one-stop shop for private applications. Another example is the Mina ZK apps protocol, which is currently deployed in testnets, I believe, for Mina. And they are taking the opposite stance on how much on-chain compute to provide to applications. In particular, they are kind of taking the paradigm of off-chain maximalism to its natural conclusion. Applications have a constant fixed number of data slots available to them, which I believe when I was looking at the docs is 8. So you have eight places to put data for a particular application contract. So if you only need up to 8 pieces of data for your application, then great. Otherwise, those should probably represent Merkle state roots of some sort that can then be referenced from the private programmability logic and off-chain computation. So kind of two extremes of the axes of on-chain compute provided by a validator set. And finally, last example protocol that kind of is, I would say, closest to Zcash in their basic design and philosophy is the Penumbra protocol, which provides not generic programmability, but some decentralized finance applications specifically designed by the protocol without providing a generic programmability layer for application developers. And so they just take the stance of providing specific applications at a high quality of security and privacy, while eschewing kind of generic availability of programmability to developers. Okay, so now we'd like to return to this question of off-chain versus on-chain computation and single-party versus multi-party computations. So there's a really interesting question here, which is, you would really like, in an ideal world, to have full computational ability over private inputs from multiple parties in a way that doesn't reveal the private inputs or the intermediate computations. And so the question is are there ways to accomplish this in a cryptographic way using good cryptographic tools with good security properties? The fact that I'm showing this slide suggests that there may in fact be such a thing. And in fact, we've seen many examples of this when we looked at various protocols that we studied. We're calling this this kind of intermediate mode of computation mediated computation. And the idea is that some types of cryptographic protocols or other nice designs allow parties that are involved as operators in the protocol to conduct these computations over private inputs, while providing fairly reasonable assurances that the privacy of the inputs is maintained even from the computational nodes. This mediated computation does in fact accomplish private computation over inputs from multiple parties. What we found is that in order to accomplish this, generally additional security assumptions had to be made. So this could be something like an honest majority assumption, or the security of particular hardware configuration. Generally, the designs mean that the security assumptions control the privacy of these computations, but not the correctness of the underlying applications, which is an important distinction to make. So usually the global computation phase, the kind of verification of ZK snark proofs and signatures and the like on the public network, are able to handle kind of correctness issues of applications. So kind of these higher security assumptions for mediated computations don't involve security assumptions on somebody being able to spend your coins or something like that. The main techniques that we've observed and most commonly deployed for implementing a mediated computation phase. First of all, trusted execution environments get a lot of runway here. TEEs, the kind of SGX is the most common architecture that you see out there, allow some assurances that the computations being done are correctly executed and done in a private way, as long as you trust the security of the hardware underlying the computations. Advanced cryptographic methods such as secure multi-party computation and fully homomorphic encryption provide a more cryptographically based method to achieve private computation over private inputs from multiple parties. Typically, these are where you end up with honest majority assumptions on the compute nodes. And so this is additional security assumptions for the privacy that you end up with. Finally, another technique that comes in various contexts to various degrees, just some notion of delegated trust, where perhaps a user decides that they are willing to trust one or more parties in the community if they know who they are, or they have a legal agreement with them, or the parties are known to have a good reputation. Then they can be trusted to act on the user's behalf and preserve their privacy. And these techniques are not isolated. Sometimes they can be combined in interesting ways as well. So this is kind of the picture of the landscape of what we've seen. And in the second half of the talk, Ying Tong will talk about some more specific examples of what we've seen here. One particular example, the reason why I wanted to bring up Penumbra in particular, is that Penumbra makes use of a very restricted mediated computation phase in one of their decentralized exchange features, which is they provide sealed bid batch swaps. So they have a functionality for a decentralized exchange with automated market makers, liquidity providers, and in particular to provide privacy to users making use of this decentralized exchange. They allow users to batch their swaps together. So over a period of a block or several blocks, the swap requests from various users are aggregated into a single overall swap, which just sums the inputs assets all into a single data value, and then some threshold decryption scheme allows the validator set to see only the batched amounts of the swaps, which provides some amount of differential privacy to the user's inputs to the swap operation. And I think Ying Tong will give some more details about that shortly. So one last feature that we took some time to develop in formulating our framework for this privacy-preserving computation is an ideal functionality, which gives some more details on how these different pieces of computation might come together in this sequence of steps, from independent computation to a mediated computation that is multi-party, and then to the global computation. This is designed as an ideal functionality in the vein of the simulation paradigm of security. So a real protocol then takes a look at how their concrete protocol realizes this ideal functionality by essentially showing that the real protocol can look exactly like the ideal functionality with an extra simulator layer on top. But the ideal functionality provides basically some hooks for concrete protocols to specify what information is expected to be leaked by the operation of the protocol, what exactly the computation steps are in the mediated computation phase, and what the security assumptions are for the privacy preserved by the mediated computation phase, with the hope being that that protocols can fill in the blanks, fill in these hooks for the ideal functionality, and use that as a starting point for understanding how the protocol's security and privacy properties can be better understood. So next, Ying Tong is going to talk about some specific protocols that we've analyzed in terms of, in particular, this three-phase model of computation. Before we do that, we have a quick pause for any questions. Okay, I see one here. So it seems like having privacy of inputs for private zero knowledge is a fairly niche use case and more difficult to achieve due to the requirement for generic MPC. And can you explain why this feature factored heavily into the SOK? Privacy of inputs for private zero knowledge. What are the primary applications for privacy of inputs, and why are these applications important to design for? Ying Tong is going to get to this in just a little bit. One of the things that we ended up deciding to do to focus our analysis of protocols was actually to focus on a specific application, which is the limit order auction. And the idea of a limit order auction is that you have input assets of some various types that you would like to trade for other assets at some specified types of prices. And so the independent computation phase, kind of the off-chain computation, is just witnessing characteristics of the assets that you have. and kind of preserving the privacy of the assets, of course, is an important factor in any shielded asset pool. And just being able to represent the kind of existence of assets of a particular type in a way that doesn't reveal that those assets is like, that's the independent computation phase. That's what it's trying to accomplish. So the mediated computation phase is then what happens after that, when you have orders from multiple parties that need to be matched together in a nice way that produces an output that is transactions that are actually finally decided upon, that satisfies everybody's requirements in terms of price. And so the mediated computation phase is actually the component of the overall architecture that we think has the most interesting design space right now, in terms of just the variety of techniques that are available, that people are developing in order to accomplish this. And ZK kind of is like the underlying bedrock that is needed for this kind of you need ZK proofs in order to prove validity of computations at various phases throughout the protocol design. All right, and no other questions so far. With that, I think I will hand it off to Ying Tong.
Thank you. So after we established this three-phase computation model, independent, mediated, and global computation, it became very clear, as Bryan mentioned, that the differentiating factor that we could use to classify these privacy protocols was the mediated computation phase. And from the initial unstructured list that we started out with, there emerged a very natural structure when we just focused on the mediated computation phase. So over here, this is one of the tables that appears in our SOK, where we're looking at the protocols in terms of whether or not they provide full programmability or general purpose programmability versus a specialized functionality on one axis. And on the other axis, we're looking at the sort of guarantees that are underlying the privacy in the protocol. So what are the security assumptions that the protocol is making in order to guarantee a level of privacy? And as Bryan mentioned previously, these guarantees are not for correctness. So for example, in Penumbra, if a threshold of validators colluded to decrypt an individual swap, then they could do no more. In other words, they could not change the swap. They could not forge it. All they can do is leak it. So this axis on this vertical axis is making very clear the assumptions for privacy that are used in each of these protocols. So in the SOK, we decided to zero in on a specific motivating application, that of limit order auctions. And let me just sort of go through the most basic variant of this, which is the order book. So this diagram might look familiar if you were at the ZSA Swap talk right before this. Basically, an order book allows users to submit orders for asset swaps. So the user inputs the asset that they are selling and also the asset that they expect to get out of the trade with the corresponding amounts. And then there's a matching process whereby complementary orders are matched up in order to form fulfilled orders. And these are also known as balanced transactions or balanced actions, which can then be submitted on chain. Now, why we chose the limit order auction as a motivating application is for two reasons. The first is really just to limit the scope of the study with the huge range of protocols and the huge range of applications. It can get quickly intractable to survey the space. And we think limit order auctions are of interest to almost everyone in DeFi. And then secondly, limit order auctions are sort of the minimal example that still captures the interaction that is interesting in mediated computation. So namely, the fact that there has to be a computation done over private inputs from different parties. And furthermore, that the result of this computation has to be atomic. So focusing on limit order auctions allowed us to both limit the scope of the study, but also zoom in on the actual interesting part of the mediated computation. Another variant of limit order auctions is the constant function market maker, and this is very popular on public blockchains such as Ethereum. This is also what Penumbra allows us to do. So what's changed from the order book example is that the amount of the output is not specified by the user. But in other words, the price is not specified by the user. And in fact, the price is determined algorithmically and publicly by what's available in the liquidity pools. So what in the CFMM case, because the price is public, by monitoring the price changes, we can trivially reverse engineer what the order was. And this is very important to keep in mind when we go over some of the protocols later on. So the best we can do in the case of CFMMs is anonymity, unless we introduce batch auctions. So we'll see later on how that's done. So you saw just now the ideal functionality for the 3-epoch model, computation model. In our study, we wrote up 4 exemplary protocols in depth. So ZSA Swap, Renegade.fi, Secret Swap, and Penumbra were found to be the representative examples for each of the classes of protocols. And they had implementations or proposed implementations for limit order auctions. So we wrote up UC style definitions for each of these. And we won't go through them in detail, but let's go through them at a high level, just to show you the amount of variance in the design space, even after we limit the application to just limit order auctions. So ZSA Swap and Renegade.fi here, they both implement order books, and Secret Swap and Penumbra both implement CFMMs. Now, I want to talk about the high-level takeaways first, the punchline, and then we'll go into each of these examples. And so that'll be easy for you to map the examples back onto these high-level takeaways. So in looking through these examples, we saw that the fundamental trade-off was between security and expressivity. Maybe this is not a surprising observation. The scarce resource is always on-chain compute. And so if your mediated computation is fully in protocol, fully on chain, that means all the nodes in the protocol are involved in it. And therefore, you have to be careful of the burden that you're placing on these nodes. Effectively, an in-protocol mediated computation is happening in a resource-constrained setting. For example, we'll see later that Penumbra makes its validators responsible for a threshold homomorphic for homomorphic addition on threshold homomorphic encrypted ciphertext. And this is a very simple computation. If Penumbra wanted, say, to generalize this beyond addition to FHE, that would place more burden on its validators. Maybe it would need to have fewer validators, very likely. Another example is Renegade.fi. We'll see later that the Renegade.fi protocol consists of multiple two-party computations. And right now, the two PCs are doing a very specific matching algorithm. Once again, if they were to generalize this to some like general purpose virtual machine, that would be way more expensive to PCs, and they probably have to run those less frequently. Now, yeah, so if we don't want to pay the cost of in-protocol mediated computation, we could opt for extra protocol, which is cheaper. But now you're outsourcing the privacy guarantees to the application designers. So the privacy guarantees are no longer the same as your network security guarantees. Instead, it's equivalent to sort of instantiating your own 2PC or your own validators outside of the protocol just for your application. And furthermore, the extra nuance comes in when interacting with the anonymity set of L1. So we need to be very careful about preserving a unified anonymity set. And yeah, naively, if we fragmented the state of the node commitments into like siloed rollups, then that would, yeah, just reduce each application to its own anonymity set. Yeah. So the high level observation is also not surprising. Whenever there's a trade-off, a decision must be made, and the decision here absolutely must be informed by the application. So which invariants are necessary for your application? So in an order book, we want, for example, price efficiency. In the CFMM, we want front-running prevention. And there's this tension between optimizing for a single application and its invariants versus enabling general applications. And we'll have more thoughts on this in the conclusion, but I think it's a valuable exercise to build some intuition by going through some actual protocols. So now, yeah, our first two examples will be ZSA Swap and Renegade.fi, which are both order books. So ZSA Swap we just saw in Cadet's talk, but to quickly go over it again. In the independent computation phase, it looks very much like a normal Zcash transaction in which you're just spending a note. In the mediated computation phase, you're specifying sort of the intended outcome of your trade, the ZSA swap action, and as was mentioned in the previous talk, this matching of orders is extra protocol, and it's unspecified in the ZSA swaps protocol. So No, as mentioned previously, whoever's doing the matching must see the details of your order. So this could be a centralized operator. So I want to mention here also that if we wanted to bake it in to the protocol, for example, make it the responsibility of all the nodes to do this matching, then yeah, we would be revealing this order information at the protocol level. So this mediated computation that's currently extra protocol produces balanced transactions, balanced swaps that are then submitted to the blockchain and settled as in a normal Zcash transaction. So Renegade.fi looks very similar in structure. What's different is that the mediated computation here is done by a 2PC matching. So basically there's this handshake protocol, there's this privacy preserving two-party computation that produces a match if the orders are complementary and does not reveal any information otherwise. These two parties also collaborate in producing a snark proof that they did a computation correctly. So yeah, the point here is that people who opt into Renegade.fi are opting into this gossip protocol, this handshake protocol, this 2PC and collaborative snark. And this collaborative snark is verified then in the global computation. So this 2PC matching is very much baked into the protocol for Renegade.fi. But notice here that the independent computation and global computation still look pretty similar to Zcash. So Renegade.fi under the hood, they do use the commit nullify architecture that Zcash does. And what's changed in the global computation is that they're verifying more proofs like collaborative snarks. They're verifying like yeah, a bunch of bespoke proofs similar to how ZSAs would introduce more proofs, or it would alter the relation that the network is verifying. Now, the next two examples are CFMMs. And once again, they'll be very similar in shape. So secret network runs on a network of trusted execution enclaves. And how you would do how you would do a limit order auction there is you would encrypt your trade to the TEE's secret key. To the TEE. And inside the TEE, they will execute your encrypted trade. So inside the TEE, they'll decrypt your encrypted trade and execute it. So it's important to note here that the liquidity pools are still public. And so after the execution, the result is updated in a global computation and can only be decrypted by whoever owns the outputs of the trade. So what's important to note here is that this change in price after the trade is public. And therefore, if your transaction was the only transaction in the block, then just by observing the change in price, I can recover the details of your order. And that is actually a similar story as Penumbra. So Penumbra is also doing a CFMM style limit order auction. So over here, instead of encrypting to a TEE, you're encrypting to a threshold of Penumbra's validators. And these validators are economically staked. So as mentioned before, this is deploying the network's economic guarantees for the purpose of this specific computation. And for the purpose of preserving privacy in this computation. And here, if a threshold of validators colluded to decrypt your swap, then they could front run, but they couldn't change your swap. So the mediated computation phase that all the validators participate in consists of a very simple homomorphic addition that's done over the ciphertext. So the point here is that we're batching all the orders for the same pair into a batch order. And so your privacy is as good as the size of the batch. And once again, if you're the only order in your batch, then will be very obvious from the price changes to recover your order. So the batch swap is decrypted by a threshold of validators and then publicly executed against the liquidity pool. And then later on, individual users can claim pro rata their share of the output by proving the inclusion of their original order in some block. So recommendations for Zcash. I think, Bryan, should I hand it over to you here?
Sure, I'd be happy to chat about this a little bit. Yeah, so in the direction of recommendations based on what we've studied for the Zcash community. The first observation from a lot of these protocols is that really only very limited kind of L1 consensus changes are needed to support generic ZK snarks and flexible data commitments that are needed for a programmable privacy development environment. Just making a more generic snark verifier and perhaps verification for certain types of signatures are basically all that you need in order to provide just the bare minimum baseline for programmable privacy on the network. The commit nullify privacy still remains state of the art for off-chain, on-chain computation. And there's really a question about what the best trade-offs are for Zcash in particular, in terms of what degree of programmability and what on-chain resources to dedicate to generic programmability. For the question of on-chain data storage, we think that it is probably worth considering mechanisms to support time-limited or metered storage. This is its own research question, of course, but it is an important consideration when you're considering increasing the surface area of on-chain data storage. To support a good developer experience, it is definitely worthwhile to provide a domain-specific language and high-level tooling of some sort for private computation. There are pre-built options available from various places in the ecosystem and other infrastructure. Obviously, Zcash has its own infrastructure for snarks and developer tooling, but focusing on the development of a DSL that has the ability to round off the sharp edges of any underlying cryptography that are involved seems to be a common theme for programmable chains, and seems to be important to kind of hide the complexity of the cryptography that's needed to implement these in practice. And finally, we think that including some kind of first-class support for mediated computation is important in development going forward. in particular, many protocols out there are integrating some kind of mediated computation layer in order to support private computation for multiple parties' private inputs. And especially in DeFi applications, this seems to be a very important consideration. We think that secure multi-party computation based mediated computation layers show a lot of promise and seem to be underexplored as a mechanism for generic programmability in a privacy-preserving way. The tools for MPC have been advancing in terms of their flexibility and efficiency over the last number of years, and we think that there's some really good potential to devise an MPC-based mediated computation layer that could be very performant and usable. This is another question for the Zcash community. How much of this infrastructure does Zcash, the Zcash Foundation and the kind of core software want to provide for users or for developers, as opposed to leaving that to developers to implement on their own? And this is a discussion that is important to have amongst a variety of stakeholders in this community. So that's the picture for our broad recommendations. Ying Tong, if you can click this forward. So two things that we're going to be putting out there sometime in the next several weeks. First of all, we're putting together a blog post with some more detailed recommendations that'll be going on the Zcash community forum as a starting point for continuing discussions. And we hope that you'll be able to join us in talking about these questions. There's a lot to discuss and a lot of both high-level considerations and technical details that go into it. We'll also be putting a preprint of our SOK paper out on the ePrint archive. And so keep an eye out for that, and you can see more about the detailed analysis of these protocols. And we hope that you can help join us for the continuing discussion about what the right path forward is for implementing some type of programmability in the Zcash ecosystem. And also interesting research questions regarding how these designs might be implemented for Zcash's architecture and in a very high standard of security. So, and I think that's it. Thank you. And would be happy to answer any questions if there are further questions. Okay, we have a question here. How does shielded programmability intersect with plain programmability in terms of software engineering? And what are the research areas that you envision that will need to be explored to make shielded programmability possible?
I
yeah.
think in the context of Zcash, especially, like the strength of the Zcash protocol is its huge anonymity set, and it is not trivial to preserve this anonymity set across multiple applications. So yeah, I think this is one sort of design difficulty in shielded programmability that we don't have in plain programmability. This tension between wanting full expressivity for your application versus wanting to still be part of the anonymity set and to be able to compose with other applications. I think the compromise that Aztec made is that they allow for public calls. So like cross-application calls can be public because otherwise I think only a very limited class of applications would be viable if all applications had to compose fully privately. But I think this is definitely a very important design question, like how do we introduce programmability on Zcash without fragmenting the anonymity set, while still allowing for interesting applications with meaningful composability.
And I do feel that the design of a domain-specific language for implementing these private programmability applications is like deeply connected with these questions of what the computation model is under the hood. So looking at other projects that have developed DSLs that are designed to abstract away these questions is like a really good starting point. So Aztec's Noir language and Mina ZK apps have their snarky JS. I think it's called O1 JS now. But I do feel finding inspiration in these projects that have taken some time to understand the kind of synthesis of off-chain and on-chain computation and abstract that is a good place to start.
And personally, I think ZSA Swaps is a very good motivating application to start like larger discussions about programmability. So I think ZSA Swaps, the previous speakers had proposed, further changes to the relation to capture like the atomicity of the swap, etc. Yeah, so a different approach would be to just allow for like a separate ZSA swap application to be uploaded. And then nodes could be spent like according to that application. This basically alio exactly. But doing so in a way that doesn't shrink the anonymity set of the ZSA swap users. So yeah, I think ZSA swaps would be a great starting application that motivates like the future of programmability on Zcash.
All right, we have looks like one more question, which is probably the last we'll have time for, which is what do you consider the important features of a programming language or DSLs for generalized shielded programmability?
I think for me, top priority is safety. So we said just now that the moving the privacy guarantees extra protocol places the burden on the application developers. And for example, in MPC, it's not the case that every MPC circuit guarantees non-disclosure. Over like a set of data, you could write like a trivially disclosing MPC computation. And that is also true for like, even if you use ZK snarks, you could still like trivially de-anonymize or like just violate a lot of the invariants that a user might have been taking for granted. So a user or an application writer. So I think having a DSL that it's kind of like how Rust keeps us safe from like accessing memory that we shouldn't. So writing a DSL that very strongly guides the user away from de-anonymizing or like disclosing patterns. I think that would be like the #1 feature I want.
Alrighty, and I think that is all the time we have for our session today. So thank you again for the opportunity to speak today. I guess we'll be on.
Thank you, and thank you, Audiovisual Club.
Yeah, absolutely. This has been very well run as a conference.